Let's talk about the ideal gas law. PV equals nRT. You can find a lot of information about an ideal gas in a container using just this equation. So let's start with an example. Suppose that I have a gas at pressure of 1 atmosphere, and we will have 1 mole of the gas, that's what N represents, and I want to know what the temperature is. Well, I need to know the volume, so let's just assign a volume and say 9 liters. The only other thing left is R, which is Boltzmann's constant, and the Avogadro constant together. And Boltzmann's constant, along with Avogadro's constant, is called the gas constant. So this R is the ideal, R is the ideal gas constant. And if you want to know where it comes from, that's why I said Boltzmann's constant and Avogadro's constant, that's where R comes from. It's just combining those two things. You might remember, Avogadro's number back from basic chemistry. So trying to relate it to something familiar. That constant, the units need to match what was given in our problem. So in terms of atmosphere, mole, and liters, I just went and looked this up. The ideal gas constant in units of atmosphere, mole, and liters is 0.08206 liter atmosphere over mole Kelvin. Alright, now we're ready to go. If I'm looking for temperature, I just solve the ideal gas law for temperature, PV over nR. And then if I put in these numbers, 1 atmosphere, 9 liters, 1 mole, 0.08206 liter atmosphere, mole Kelvin. You can check out my units to make sure I do in fact arrive at Kelvin for my temperature, and from that I get 109 Kelvin. Let's say we wanted to convert this temperature from Kelvin to Celsius. Well, the Kelvin and Celsius scale are off by a constant from each other. They use the same amount of increment. So if I go up by a certain amount if I go up 1 degree Celsius, then that means I've gone up 1 Kelvin. So I need to know what that constant is. And if I just go look it up, I find that they are off by 273 on their zeros. So just because I go up by 1 Celsius and 1 Kelvin, those increments are the same. The 0 points are not set the same. So on the Celsius scale, we set 0 at freezing water. But on the Kelvin scale, we set 0 at the least possible amount of molecular motion. So Kelvin, 0 at lowest possible atomic motion. And that off by number is 273. So what does that mean? So if I have a number in Kelvin and I want to go to Celsius, so let's call that C equals K minus 273. So if I have a temperature of 109 in Kelvin and I want to go to Celsius, C equals 109 minus 273. Grab my handy dandy calculator. I do 109 minus 273. I get negative 164 degrees Celsius. The Fahrenheit scale is a bit different. So Fahrenheit has not only a different 0, but it also has a different increment. So if I go up 1 Fahrenheit, I haven't gone up 1 Celsius. In fact, the full formula for that, make sure I've got my paper centered on the camera, the full formula for that is Fahrenheit equals Celsius times 905 plus 32. So going up 1 Celsius is going up 9/5 of a Fahrenheit, but they also have a different zero. So Fahrenheit has water freezing at 32 degrees Fahrenheit, whereas Celsius has water freezing at 0 Celsius. So I've already got this in Celsius. I can do F equals negative 164 degrees C times 9/5 plus 32. And I find that this is negative 263 degrees Fahrenheit.